Yes, sir. Yes, sir. Yes, sir.
Sir, we'll
Yeah.
start the program.
Yeah. Yeah. Yeah, boss, you can start.
So, good morning to Dr. Vikram and good evening to our participants. With immense pleasure and great privilege, we welcome our speaker, Dr. Vikram Mehta. Currently, he is the Executive Director of the Center for Research on Changing Health System. Uh, a strong interest in more application-oriented research, scientific research led him to do PhD degree in meteorology in University of Florida. After that, he worked as a research scientist for more than 12 years in NASA, and his area of specialization is decadal climate variability. Strongly motivated to use climate science for social benefits, Vikram founded the Center for Research on Climate Changing on Earth Systems. It's a non-profit and a scientific research organization that was established in 2002. And he has received many research grants from NASA, NOAA, and some other well-recognized funding agencies to work on that climate decadal variability and societal impacts. Uh, Vikram has worked extensively on assessing, modeling, and predicting the decadal climate variability impacts on water resources, agriculture, and waterborne transportation in Mississippi River basins. He has published many research books, many books and research papers. This year also, he has published a book, Decadal Climate Variability Science and Predictability, which was published by CRC Press. Vikram has published more than 150 research papers, and he has contributed not only in USA but also in India. He is the founder of Indian Center for Climate and Social Impact Research in Ahmedabad. His hobbies are flying single-engine aeroplane and reading books and listening Indian and Western music. With this brief note, I request Dr. Vikram to deliver a lecture. Thank you, sir.
Well, Dr. Vijay Bhaskar, thank you very much for that very kind introduction.
Thank you, sir.
You might also have mentioned that you and I first met when we were both working in the Indian Center for Climate and Societal Impacts Research in Ahmedabad, and that's where we met for the first time. Anyway, so good evening to all of you, and I'm very happy to give this lecture. So you can see, I'm going to focus on decadal climate variability and its impacts on India. And then at the end, I will try to, outline some actions which need to be taken. And so all of you can, join in that. So this is going to be the general outline of my talk. I'm going to start with outlining the water and food needs of the world, and then very briefly define what is climate variability and what is climate change. Then talk about natural decadal climate variability phenomena and mechanisms, and then go into impacts on India. I may not be able to show everything, but I'll try to just focus on India as much as possible. And then at the end, talk about needed programs in education, research, and applications. So let's start with the overall big picture.
Sir,
Yeah.
your presentation is not visible, sir.
What?
Your presentation is not visible here.
Uh-oh. Okay, let me start again.
Yeah. Now it's visible, sir.
What?
Yeah.
It's fine,
Yes,
sir.
sir. It's okay now. Yeah.
It's okay now?
Yeah, it's okay, sir. It's okay.
But I need to see it too, otherwise I can't. Okay, so what about now?
Yeah, it's okay, sir. Visible, sir.
Now?
Yeah.
Can you see?
Sure.
Can you see?
Yes, sir. Yes, sir.
Yeah.
Okay, so let's start. So this is the outline, and I'll try to show things which are pertinent for India mostly. Okay, so let's start with the overall worldwide picture. Can you see the slide now?
Yes, sir. Yes, sir.
Very good. Okay. So this is an estimate of the annual renewable fresh water per person. The one on the left was actually made in 1995, and at that time they made the projection for 2025, which is on the right. And just to give you, some sense of what the colors mean, more blue is the color, the more water there is available. But as you go towards yellow and then to red, then the water availability becomes less and less, as you can see. So 25, the projection for 25, you can see large parts of the world are yellow and red. And actually, where you are in southern India, it is already likely to be red pretty soon, meaning that there's going to be water scarcity in much of southern India. Also, northwest India, you can see Pakistan and other parts of the world. So that is so far as the fresh water per person is concerned. Okay, availability of fresh water per person. Now, what about food and electricity production? So the world's population right now is about 7.5 billion people, out of whom about 1 billion are chronically undernourished. They don't get enough food to eat, or they don't get food which is nourishing. So they are chronically undernourished. Now, as you look forward, we are in 2020. 30 years from now, the world's population is projected to be close to 9 billion people. Okay, so 30% higher than what it is today. And nearly the entire increase will be in developing countries such as India and the Indian subcontinent in general. So the food production needed at that time will be 70% higher than now, because not only you have all these people you have to feed, additional people, but because so many are already chronically undernourished, you need to produce much more food so that everybody can be provided food. So the cereal and meat production, etc., has to increase by very large numbers, and the electricity production needed 30 years from now, or over the next 30 years, increasing gradually, would be about double from what it is today. Now, what about water in 2050, so 30 years from now? So I showed you the previous map in 25. You can see there were large areas of yellow and red. Now you can see the projection for 2050 is most of the world is red, yellow or red. And what this means here is that if you have, let's say, red, most of India is red, and that means greater than 50%. What does it mean? That the withdrawal of fresh water is more than half of the recharge rate. So, it is not sustainable, because if you keep drawing more water than what is going in, then, excuse me, any problem?
Sorry to interrupt you, sir. Slides are still not visible, sir. It seems like. Now it's visible, sir. But the slide show it's not visible, sir.
Okay. Hold on.
You might have to select presenting slide. I mean, when you click present now, you might have to select a window and select slideshow instead of slides. That might solve this problem.
Okay, let's see. I'm sorry about this, okay?
No.
No, but this only shows, okay. Hold on, okay? How about now?
Much better, sir. Yes, sir.
You can see it now?
Yes, sir. We can see it full screen.
Okay, good.
Thank you.
Okay, so as you can see, most of the world would be red in 2050, 30 years from now, because of water stress. And what, most of India is red, and what it means is that the withdrawal rate of fresh water, it would be higher than 50%. So that means that you are withdrawing more water than you are recharging with. And so that is not a sustainable situation. And we'll come to this towards the end. But we also know that water, other things like food security, energy security, public health security, they are all dependent on available water. So water is important not only for itself, but also for food, energy, health, etc. And so if you have problems in freshwater availability, it will create problems in so many other things. So the situation as it is developing is very serious. Now, you have all heard probably about the UN Sustainable Development Goals, and the ones which are pertinent to climate are listed here. Hunger, health and well-being, we just talked about it. Clean water and sanitation, we just talked about it. Energy, we just talked about it. Then industry, innovation, infrastructure, sustainable cities and communities, of course, sustainable, consumption and production, climate action to mitigate and adapt to climate. Then also life below water means, fish and shrimp and other crustaceans, other life, in the oceans, in the rivers, in the lakes, life on land, meaning vegetation, animals, birds. So there is also, so if we can make progress on climate and water, we can make progress towards all of these UN Sustainable Development Goals. Then also, as you know, for example, in southern India, there have been, massive floods recently, and huge disaster because of the floods in cities. Also in rural areas, because if the fields are flooded, farmers cannot grow any food. So there is a so-called Sendai framework for disaster risk reduction. And so climate also plays into causing disasters and increasing disaster risk. And so if we can make progress in climate mitigation and adaptation, we can also reduce the disaster risk because of climate. So understanding it, strengthening the risk governance to manage the risk, then we have to invest human and material resources in disaster risk reduction for resilience, and we have to increase or enhance disaster preparedness for effective response. So this is the large scale sort of background that I would like all of you to keep in mind, because whatever we do in the future, all of these things will be very, very important. So the work we are doing, for example, in environmental science, plays into all of these important goals and the framework, etc. And so when you are working on something, the going becomes difficult at times in research, even in teaching. Please keep in mind that you are contributing towards achieving these goals and in reducing the disaster risk for the world. Okay, so you hear about weather, you hear about climate, you hear about climate change, climate variability. So what do all these words mean? So I thought that I would start with the traditional definition of climate. Traditionally, climate has been defined as 30-year averages of precip. So in India, it's mostly rain, except in the north, it's also snow. So 30-year averages of precip and air temperature at any location on the surface of the earth. This was the traditional definition of climate. But it has evolved over the last 20, 30 years. And now, even averages over shorter periods, down to even 3 months, are considered, climate, and includes not only precipitation and temperature, but also near surface winds and humidity, sea level pressure, soil moisture, sea surface temperature, and other variables are included now in the definition of climate. So now you can ask, what is weather then? So weather is the day-to-day or week-to-week variability of these variables. Precip, temperature, clouds, winds, and storminess, something that we experience every day or within a week or so. And so one can say that weather is the instantaneous realization of climate. what you see today is weather. What you see over 3 months, 6 months, 10 years, that is climate. But both climate and weather at any location depend on latitude, longitude, altitude, land cover, and how close the location is to oceans or seas and other large water bodies such as very large lakes, rivers, etc. Okay, so these are the definitions, current definitions of climate and weather. So please keep them in mind. So now, what is climate variability and what is climate change? So we define climate variability as rainfall or in general precipitation and temperature undergoing cyclic or near cyclic variation. So for example, temperature, let's take temperature. Every day you see the temperature going undergoing cyclic variation, that it's relatively warm, let's say in the afternoon hours, and then it's relatively cool after midnight or so at night. So you see these cycles taking place every day. Then you also see the annual cycle, that temperature, rainfall, etc. They undergo annual cycle. So that is also climate variability. But these two are driven by changes in solar radiation taking place over a day because of the Earth's motion, as well as Earth's rotation, as well as motion around the sun. But then there are, as we will see, there are other climate variability phenomena which take place because of interactions within the Earth system components like ocean, atmosphere, land, and also variability in solar radiation, etc. So that is climate variability. So it's like cyclic or nearly cyclic variations. And I'll show you in a minute, I'll show you examples of both. So now, what is climate change? Climate change is rainfall or in general precipitation and temperature undergoing a unidirectional change. That is, when the climate variables either only increase over a long period of time or decrease over a long period of time. Now, what is meant by long period of time is very subjective. It depends on what time scale you are interested in. For example, if you have a 10-year cycle, for the first about 2 to 3 years, you see an increasing trend. But that is not climate change, because as you know, if you know that this is a cycle, you know it's going to come down. When we see, for example, the annual cycle, from let's say from about February, March to June, July, August, we see the temperature continuously increasing. But we know that it will come down because it's a cycle. It is not climate change. It's not going to be permanent. It's going to come down again. So these are very simple definitions of climate variability and climate change. So please keep that in mind. And both of them are important. For example, in the news media, in people's mind, climate equals climate change. And that also because of increasing greenhouse gases in the atmosphere. But remember that natural climate variability has been going on in the Earth system for millions of years, literally millions of years. And so because of it is not going to go away, it may be modified by climate change. There is interaction between the two. But climate change is not going to completely obliterate or suppress climate variability. So the last IPCC report from the Intergovernmental Panel on Climate Change, published in 2013, makes that very clear, that natural variability will continue to be a major influence on climate, particularly in regional scale and in the near term. By near term, they mean the next 20, 30, 40 years. By mid-21st century, by mid-2050, as we saw, the magnitudes of the changes, projected changes, will be substantially affected by what happens to emissions of greenhouse gases. Okay. So climate variability is as important or even more important as climate change today and for the next at least 20, 30, 40 years. Please keep that in mind. So if there is nothing else that I can clearly convince you of today, I would like you to keep this very clearly straight in your mind, that climate is not just climate change. Presently and in the past, climate variability is much more important than climate change. So anything that people think is unusual is not because of climate change, unless proven so. Okay, climate variability is responsible for most of the so-called changes or extreme events and things like that that you see around you. So please keep this in mind. Okay, so now let's see here on this figure what is climate variability and climate change. Now there are two time series plotted here, one in red and one in black. These are two different estimates of surface temperature. Okay, sea surface temperature precisely. You can see that there are both of them have these straight lines fitted to them, and you can see both of them have been increasing monotonously, more or less, over the last 50, 60 years or so. But you can also see the variability riding on top of the climate change. And as you can see, the amplitude of variability over, let's say, a 5-year or 10-year period is much bigger than the change in temperature because of the linear trend. So please remember this, that both of them are occurring at the same time, and it is not one or the other, but it's both. Okay, so as you can see here, there are relatively short-term cycles and also long-term cycles. And the long-term cycles, you can see, have periods of approximately 10, 15 years. And that is what is called decadal climate variability. And that's what I've been working on for the last more than 30 years. And so today I'm going to focus on so-called decadal cycles, climate cycles with periods of about 10, 15 years. So what is it? So these are, as I said, these are climate cycles with about 8 to 20-year periods. And we can see these in all kinds of data, long-term data, oceans, land, atmosphere. The main causes are ocean-atmosphere interactions, land-atmosphere interactions, and also interactions among stratosphere, troposphere, and ocean, and solar variability, as we are seeing through research. Solar variability, I'm sure all of you have heard about sunspot cycles. Sunspot cycles have typically periods of 11 and 22 years. And now we are, this has been a speculation going back several hundred years that these sunspot cycles are responsible for causing climate variability on the Earth. And now we are seeing more and more evidence of this through observations, through model simulations, that indeed it looks like solar variability is playing a very important role in these decadal climate cycles. Now, there are numerous so-called phenomena that have been identified. Pacific decadal oscillation. Then in the tropical Atlantic, there is a north-south temperature gradient which oscillates at time scales from a few years to a few decades. I call that tropical Atlantic sea surface temperature gradient or TAG oscillation. There is West Pacific warm pool oscillation at decadal time scale. And there are other ways to define decadal variability, such as frequencies and intensities of interannual El Nino, La Nina events. And there are other also ways to define decadal variability. But these are some of the major ones. Okay, so what does the Pacific decadal oscillation look like? So this is the positive phase of it. And the red and the blue shows sea surface temperature departures from the climatological annual cycle. And this is the positive phase of the PDO going back to 1900. And the vectors show winds at 850 hectopascals, which is about 1.5 kilometers up in the atmosphere. And so you can see that the red is where the ocean temperature is warmer than average. The blue is where the ocean temperature is cooler than average. And the four panels show, the four, averages in the four seasons. December, January, February up in the top left, and then March, April, May, June, July, August, September, October, November. So you can see there is a distinct annual cycle to the PDO. But the pattern is quite clear that it's this is the Pacific Ocean. You can see it spans almost the entire Pacific Ocean from north to south. And when the temperature in the positive phase, the temperature is warmer than average over much of the Pacific Ocean in the tropics and subtropics, and also along the coast of North and South America. Elsewhere, you can see the temperature is below average. That's why it's blue there. And you can see that the low-level winds, at 850 hectopascals, they converge over the warm water, and then they diverge out of the cold water, as you can see. The time series at the bottom shows the so-called PDO index going back to 1900. And the red and the blue show positive and negative values of the index, and the black line is sort of a 12-month running mean of the index. So you can see that over this approximately 118 years period, there is variability at several time scales. You can see month-to-month variability. You can also see year-to-year and decade-to-decade variability. You can also see that the PDO has a tendency to remain either in negative phase or positive phase for several decades at a time. And then on top of that, you see this decadal and higher frequency variability. And as we will see shortly, this phenomenon appears to be, making worldwide impacts on water, agriculture, etc. We'll see this shortly. The tropical Atlantic, as you can see, shows the pattern of sea surface temperatures in the tropical Atlantic. At the top panel shows annual, then December, January, February, all the way down to September, October, November. So the tendency is for this gradient, so relatively, when it is relatively cool in the north, showed by the blue, it is relatively warm in the south, and then in one phase, and then in the opposite phase, the pattern flips. And you can see in the time series going back to 1900, variability at several time scales, including decadal variability, as you can see, also much longer period variability as well. So, so this phenomenon also makes substantial impacts, principally on both sides of the Atlantic, namely Africa and South America, but also in the US, in Europe, and even as far away as India. So now let's go back. How far do we go back in the data? And so as you know, these data come from actual measurements of temperature going back about 100 some years. But these measurements were not available before the 1850s. In some cases, they were available from about 1856 or so in the oceans. On land, of course, in some places there are time series. For example, in India, rainfall time series going back to 1850s, and in Europe also some parts of North America. But these so-called instrument measured data are relatively short in length. And when you are looking at cycles of 10 to 20 years, even if you have 100 years of data, you get only maybe 5 to 10 cycles. And so statistically, it would not be very significant. So then how do we know about past climate? What happened? How can we understand what happened in the past? So there are the so-called proxy climate data. And you have probably heard about tree ring data. So very quickly, when a tree grows during the growing season in spring and summer, it creates new material, which then grows around the stem of the trunk, around the center of the trunk. This new material is in some cases affected by rainfall and temperature locally, which means that you can get some idea about rainfall and temperature in that area where the tree grew. And this this is called, going back in time to understand climate using tree rings is called, very, very interesting and very important field of climate science is called dendroclimatology. Okay. So this, the same way, tree rings give you some idea about past climate. Similarly, you can also get idea about past climate from corals. Tropics, in the tropical oceans, there are corals, and there are some their chemical composition, the oxygen isotope ratio in the corals, etc., can give you some idea about what the past ocean temperature was like, where the corals were living. And there are other things like sediments in lakes. There are layers of sediments in lakes, and from them you can say what happened in the past. How were the sediments created? What was the role of rainfall in the lakes, etc., etc. So if you want to go further back beyond 100, 150 years, then you have no other choice but to take recourse to these so-called proxy climate data. And so let's look at proxy climate data over India from tree rings going back more than 700 years and see what they are telling us about past climate in India. So what is plotted here is something that is called the Palmer Drought Severity Index. This is a very widely used index of dryness and wetness. It combines rainfall and temperature information so that it's not only rainfall, but it's an index of the total dryness or wetness in a given area. And so these are tree ring based Palmer Drought Severity Index data going back to 1300 AD, okay, and coming forward to like 2005. So you can see that the positive here means when the PDSI is positive, it means wetness. When it is negative, it means dryness. So here positive is blue, positive index is blue, negative index is red. And I have marked in boxes periods of dryness in India based on these tree ring data. And you can see then the column on the right links each of these dry periods to what happened to Indian society during that period. And I did a lot of research with other literature published about famines in India during these dry periods. And as you can see, all these dry periods were associated with droughts and famine in India. It killed millions of people, as you can see, all the way down to the 1940s. Okay? Millions of people were killed every few years in these droughts and resulting famines. Since 1940 also, there have been these dry periods, but because of more food available, better transportation, better government management, people are affected certainly in large numbers, hundreds of millions of people, but the number of deaths are relatively much smaller compared to what used to happen before the 1940s, as you can see. So this is a way you can connect information from these kinds of proxy climate data such as tree rings to what actually happened to societies. And I have done this for North America, also for Europe. And the general sort of result seems to be that all of these regions have undergone this kind of decadal variability, dryness and wetness, and they have made very substantial impacts on civilizations in India as well as in North America, in Europe, sometimes triggering socio-economic revolutions, a lot of violence because of famines and droughts, changes in governments, rise and fall of civilizations. So all of that has happened. So what have we learned? That there are these prominent hydrologic cycles at various periods, indicating nearly cyclic mega droughts and pluvial. Pluvial is the opposite of drought, when you have a lot of water. Okay. So both mega droughts as well as mega pluvials in the last about 1,000 years. As I said, it has resulted in mass migrations, a lot of deaths, and political awakening in India. Also, civilizations in North America and Europe have been very severely affected by these cycles. The alternating wet and dry epochs have witnessed human migration surges and development of agriculture and cities, followed by crop failures, water shortages, economic losses and suffering, etc., etc. But it looks like all this evidence is there, but human societies are very resilient to change. We are not learning from the past. But the important thing is that we actually look at the past in various ways, whatever we can, to see what happened climatically in the past and how were societies affected. Can we learn from that how societies react or don't react to climate variability and climate change? And how can we use that information to understand what is going on now and what might happen in the future? And then either prevent adverse impacts or exploit favorable impacts. They are not always adverse. There can be, we can maybe exploit the favorable impacts also. Okay. And it looks like the PDO, which I showed earlier, that can also be, we can get some idea about the past PDO index going back beyond 1850s or even, like 1900 through tree data. And it looks like the past PDO indices going back to the 17th century show that these dry and wet epochs, both in India, also in North America, were perhaps forced by this PDO variability at decadal and multi-decadal timescales for the last at least 300 years. So we have some idea of how these climate variability phenomena have impacted societies in the past. So now coming forward, as I said, we have data going back at least 100 years in many parts of the world now. So what do they tell us about decadal climate variability and impacts on societies? So we can, now here I'm showing the red and blue is the PDO index and the black line is the Palmer Drought Severity Index, but calculated using instrument measured temperature and rainfall data worldwide. So the time series clearly shows that, and the map on the left, on the right shows, the blue is wet areas, red are dry areas, and the light brown are also drier areas. So you can see that the PDO is, associated with decadal variability of dryness and wetness in many parts of the world. And the correlation coefficient between the two is 0.77. So you can see that this one phenomenon is making such an important impact all around the world. So if we can understand that phenomenon, and if we can predict it, maybe we can prevent bad things happening and exploit the good things that might happen, meaning more rain. How can we manage water? How can we store water? And if there are going to be droughts because of PDO, how can we mitigate the impacts of droughts? So even if we can understand this one phenomenon, we can make a very large contribution to well-being of the humankind. Okay. The bottom row shows impacts of the tropical Atlantic gradient variability. So the one on the left is the positive phase of the tag, so that which means that the tropical North Atlantic is relatively warmer compared to the tropical South Atlantic. And you can see this is in December, January, February. You can see the blues are where the PDSI is positive, meaning it's wet, and the red is where it is dry. In the negative phase on the right, you can see that the signs flip, so that areas which are, for example, Africa, much of Africa is blue in the positive phase of tag, but it becomes red in the negative phase of the tag. Also, South India, you can see it is wet in December, January, February during the positive phase of tag, but South India is dry in the negative phase of the tag. So again, this is another phenomenon which appears to make worldwide impacts on dryness, wetness, on then therefore on water availability and other things. So what about river flows? Now, it is not only that data, because societies did not start measuring temperature, rainfall, simple things until about last 100 years or so. Similarly, river flows have not been measured regularly everywhere until very recently. And even where it is measured, not all the data are openly shared with other countries or even scientists in their own countries. So, for example, here you can see large areas of the world are blank because those countries do not share the data with anybody. India is one of them. But you can also see that US, Canada, Europe, Southern Africa, parts of South America and Australia, they share the data openly with others. And this shows analysis from 1961 to 2010, about 1,850 locations. And this is the principal pattern which is associated with the PDO. So when PDO is positive, you can see over much of the US, the river flows are above average, whereas over most of Southern Europe and Central Europe, river flows are below average. And then over also Southern Africa in the positive PDO phase. And you might remember going back to this figure that when the PDO is positive, Southern Africa is dry. And that is also shown here by river flows. So when you have independent measurements of different quantities, and when you get similar results, then you know that these phenomena are really they are real, and that believable. The impacts are believable. Unfortunately, India, China, so many other countries, they don't share the data with anybody, and as a result, we cannot make much progress unless the data are available. Now, it's not only it makes sense that when you have when PDO makes impacts on dryness, wetness, and river flows, it's going to affect agriculture because irrigation is expanding many parts of the world. However, most of the agriculture today is rain-fed or fed by rivers or fed by snow melt. And so it is obvious that climate variability would have impacts on agricultural production. So these are some of the crops. We have analyzed 400 combinations of crops and countries. So 20 countries and 20 crops in each country. So 400 crop country combinations. And this is what we have found in some of them. I'm just showing, I think about 10 of them because of space, but just wanted to focus on a few important cases. You can see, and here I have listed which crops are affected by the difference between positive and negative phase of the PDO. How much is the change in production? Again, the crop data are not widely available. Even within India, you cannot get crop data for, let's say, district by district or local area by local area. But the UN's Food and Agriculture Organization gets one number for an entire country of one crop or each crop per year. So they have data going back, many decades. But again, as you know, India, for example, is so vast, north, south, east, west, that one number, let's say for maize or soybean, it's very hard to try to understand impacts of climate variability or change from one number for such a large country. But there are other countries in the world, for example, the US, where you can get data to very small scales. And these are all open, free data. Anybody can get on the website and download the data and work with them. So these are some of the things that you should keep in mind. And when you talk to government officials who have data, who have these data, you should talk to them that unless you release the data, let us researchers look at them, we will not be able to help the country. So same thing about river flows and crops, for example. Anyway, so you can see that cashew nuts, maize, orange, soybean in India, very large changes in production between positive and negative PDO phases. And similarly, in other countries, you can see so many other crops are affected. So now we have seen dryness, wetness, river flows, crop production, all of them substantially impacted by the PDO variability over decadal timescale. So now let us focus or continue to zero in on India. Right. So again, we go back to PDSI, but this is from instruments, okay, going back to 1961, based on instruments. So based on rainfall and temperature measurements by instruments, and then the PDSI calculated from the instrument data, not from tree rings. So you can see the upper row shows rainfall percent anomaly of June, July, August average. On the left is the when the PDO index is greater than or equal to 0.75. On the right is when the PDO index is less than or equal to minus 0.75. And the stippling shows 95% significance of the anomalies. This is in June, July, August. So you can see when the PDO is in the positive phase, most of India is dry or drier than average. And then PDO is in the negative phase, you can see most of India is under, relatively wet. And the upper row shows rainfall. The lower row shows PDSI anomaly. You can see that is consistent with the rainfall pattern. This is for the tropical Atlantic gradient. Again, you can see substantial impacts. In this case, the phase relationship is opposite in the sense that when the TAG index is positive, most of India is relatively wet, and when the TAG index is negative, most of central and western India is dry. And this same thing is shown by rainfall as well as by PDSI, as you can see. So again, you can see consistency in the results. Now, I said that river flow data are not very easily available for India. There are some going back to the 70s, and I'm showing here one example, which is not very far from where you are, although it's substantially far, but not very far. This is Krishna River at Pondugala. And these are data from Water Resources Information System of India, WRIS. This shows time series of river flow at this one station going back to 1975. And you can see the flow varying over several time scales. And each bar is 1 year. So you can see that there is variability at approximately 10-year like time scale. Very large decadal variations from about 5,000 million cubic meters to 60,000 million cubic meters. You can see the difference between the minimum and the maximum. Huge. So these are the cycles going on in the river flow in Krishna River. But unless we have data for many stations, quality check data, good data going back many decades, we cannot really understand the impact of climate variability and in the future impacts of climate change on river flows, because without data you can't do anything. Anyway, it looks like apparently even in this short time series at one location, there is some relationship between these decadal climate phenomena and the river flows, which is consistent with the rainfall and PDSI data I showed you earlier. Okay, so I mentioned the crops. So now let us focus on a few crops. The map of India shows where these selected crops are produced in different colors, you can see. And the time series on the upper right show the red and the blue is the PDO index, and the black line is the crop production anomaly going back to 1961. And as you can see, for cashew nut, the correlation coefficient between PDO and the cashew nut production anomaly is minus 0.7, which means when the PDO is positive, you get less production, which is consistent with the fact that when the PDO is positive, much of India is drier than average. You see river flows going down, you see the dryness wetness index showing dryness. And so it is not a surprise that the crop production also goes down. You can see the same thing in corn on the right, or what is called maize in India. Again, the correlation coefficient is minus 0.64. And you can see very substantial changes in crop production as a function of the PDO index. So if we focus on three crops, let's start with soybeans on the lower left. The main production region is central and western India. As I said, as you can see, the correlation with PDO is negative, and the change in production between positive and negative PDO phase is 44% of the average. Cashew nuts. India is one of the top 3 producers of cashew nuts in the world. About 60% of world's export is from India. Main production is in central India and along the coast. It is drier in PDO plus, as we saw earlier. So therefore, it has negative correlation with PDO, as you can see in the upper right figure. The difference between production in positive and negative phase is about 50%. And about similarly, you can see corn also very substantially associated with PDO phases. Another impact, you can see, this is the Krishna River at Pondugula. You can see variability of river flow, very large variability. And as you know, there is transportation on some of these major, even minor rivers in India. And Indian government is planning to expand, to develop these waterways to transport goods and people all over the country, wherever possible. So anywhere and anytime, water is affected by climate, rivers are affected by climate, as you can see from here. And therefore, river transportation is going to be affected by climate. So here, this shows that the inland waterborne transportation map of India as it is today. So they have a very substantial network, especially in north and eastern India, also in southern India. More than 14,000 kilometers of navigable waterways, which includes rivers, canals, backwaters, creeks, everything. 55 million tons of cargo transported annually by mechanized vessels as well as country crafts. There are 5 nationally designated waterways, and you can see them here on the map. National Waterway 1 is in Uttar Pradesh and Bihar. NW2 is in Assam and in states of Northeast India, Meghalaya. That's essentially the Brahmaputra river system. NW3 is in Kerala. NW4, not far from where you are. As a matter of fact, one end of NW4 is very near Chennai, as you can see, and goes up the coast to Andhra Pradesh and Telangana. And then NW5 is in Orissa and West Bengal. So they want to expand these, and as you can see, the main cargoes are coal, petrochemicals, cement, etc. And also the tourist traffic on these waterways is increasing, and the government wants to keep increasing or expanding these waterways even further. Between summer, which is the low flow area, low flow time because the no rainfall, and monsoon, which is the high flow season, there are very large changes in water level and speeds in NW1 and NW2. And therefore, if we can predict the flows and the levels then we can compensate for changes maybe or adapt to the changes and keep the traffic flowing. Also, after the monsoon or during the monsoon, when a lot of sediments are washed into the rivers and the waterways, a lot of dredging is required to remove all the mud so that the vessels can ply again. Okay. Um, Also, deforestation. When it rains in deforested areas, the water takes a lot of silt with the runoff into nearby waterways. And that is also increasing the silt loads in rivers, canals, and in other waterways because the catchment areas and the forests are not managed properly. So you can see how intricately linked climate is to all human activities. Dryness, wetness, we saw river flows, transportation, crop production. So you can see for India, it is vitally important that we understand climate variability and its impacts on India. And then in the future, as the climate change impacts increasingly become more obvious, how to cope with those changes as well. So all of you are right in the right area to be working on all of this. And you can see that there is so much work to be done and such a multidisciplinary aspect of this whole field that you can take any part of it and make very substantial progress towards those goals that we discussed earlier in the presentation. Okay, so this is from Niti Aayog, the organization which replaced Planning Commission in 2014. So they are now talking about water insecurity. This is from a report from Niti Aayog in 2018. So they say that India is facing the worst water crisis in history. Currently, 600 million people face high to extreme water stress. Annually, about 200,000, 2 lakh people die due to inadequate access to safe water. In another 10 years, by 2030, the projected water demand will be double the available water supply. Can you imagine that? In just 10 years' time, they are predicting or projecting that the demand will be twice as much as the available water supply. So, which implies that there will be water scarcity for hundreds of millions of people and other strife that it will cause. I mean, as you know very well, the water issues between, for example, Karnataka and Tamil Nadu. So just imagine 10 years from now, how much worse those issues will become because of water scarcity. But again, I talked about not having data available to understand, model, predict. So water data systems are limited in their coverage, robustness, and efficiency. Sometimes data are not available at adequate level of detail. Data are often unreliable due to outdated collection techniques and methodologies. So if you can improve data quality, somebody can go through data and see where there are problems, flag them, clean up the data. That will be a huge service to the field. Also, a lot of states collect data but do not share with the neighboring state because rivers go from one state to another and they don't want to share data from their state because they are always fighting about water, right? And so it adds to costs and inefficient use and management of water. So there is an imminent need to deepen our understanding of India's water resources and usage and put in place interventions that can make water use efficient and sustainable. Now, mind you, all of this, what Niti Aayog says, has nothing to do with climate variability and change. They do not include that in their projections. This is just because of increasing population, increasing water uses, etc., and declining groundwater levels, declining river flows. So now add to all of these problems what might happen as a result of climate variability and change. So the the possibilities are truly frightening. Okay, and this is not like 100 years from now. This will be like 10 years, 20 years from now. So please keep all this in mind, how you can contribute towards improvement of life in India. Again, this is from the International Water Management Institute. They are saying that, again, the same sort of message that the water demand is increasing rapidly. Not available, available water will not be able to, satisfy the demand. 9 major water basins, which comprise 75% of the total human population, will be physically water scarce by 2050, and 10 major water basins, home to 80% of the population, will see their groundwater tables declining considerably by 2050. We saw this earlier in the available water in 2050, the projection for available water, that the groundwater abstraction ratio greater than 75% by 2050. Again, these projections do not include impacts of climate variability and change. So just imagine how bad the actual scenario might turn out to be beginning, soon. Because 5-10 years in the life of a nation, 5-10 years is like the blink of an eye. It will go very quickly, this period. So the time to do something is now. So how can we make progress in India-specific issues? So we need accurate estimation of local, regional, and national surface and groundwater resources and how the water is used. Then we need to develop understanding of how and to what extent water supply and demand drivers impact water resources and various spatial and temporal scales. I mean, one of the major demand driver is agriculture. So just mindlessly pumping out groundwater using electricity to pump out groundwater and putting it out in the fields where much of it evaporates, it's a waste of a very precious resource. So we need to understand how these various drivers of water supply and demand are impacting the available water resources. Then we need to develop sound science and use that to educate politicians, bureaucrats, students everywhere from elementary school to graduate students, and also the general public about the current state of water security in India. We have to take everybody along. Scientists have to be the leaders, and it can only be if the science itself is sound. Also, at some point there has to be prioritization of water usage among drinking water and other domestic, agricultural, industrial, other uses, other sectors of the society. Because everybody cannot keep wasting water whichever way they want to. So there has to be some priorities. So we need sound science-based development of projections about future water supply, demand, and access. The politicians may not want people to know, but it is scientists' duty to do this work and educate everybody as to what are the likely scenarios. Then how do you adapt to them? So development of adaptation options under various driver scenarios. Assessment, monitoring, and prediction of multi-year to decadal droughts and their impacts on water and food securities. And then go one step beyond that to development of models and methodologies to simulate and predict socio-economic impacts. What might happen if the water crisis between Karnataka and Tamil Nadu becomes much worse in the next 10 years? What might happen to the societies there? Will there be violence for water? I know in some cases there is already violence for water, but will it become much more widespread and much more violent? So we need models and methodologies to simulate the situations and then to predict what might happen. So for all of this, we need to assess what are the data and information needs of farmers, water managers, government officials, other stakeholders, and we have to develop decision support systems so that they can access the data and make the decisions for their applications based on sound science and real data. And yeah, so the IPCC scenarios for future climate also talk about, persistent droughts, even multi-decadal droughts in many parts of the world over the 21st century. Um, so these are actually, more alarming scenarios. As I said, those projections by Niti Aayog and the International Water Management Institute, they do not, they do not include potential impacts of climate variability and change, whereas these are from climate models. So you can see when you combine everything, the possibilities are truly frightening. We might, in the worst case, India might go back to millions of people dying every year in famines. A scourge that was eradicated after India became independent might happen again in the future. So then, there are, as you step back and look at the entire world, we need to do a lot of, make a lot of progress in various aspects. And it's generally a more sort of generalized program that I have listed here. So in summary, I showed that decadal hydrologic cycles impacted civilizations for at least the last 700 to 1,000 years. Natural decadal climate variability phenomena are causes of the decadal hydrologic cycles. There are substantial worldwide impacts on water supply, demand, crop production, inland waterborne transportation, hydroelectricity generation, because I showed you the flow in the Krishna River at that one measurement station. So if there are dams on the river to produce hydroelectricity, you can imagine that these changes, such large changes in flows over 10, 15 years, make a huge impact on hydroelectricity generation in those areas, and also on other societal sectors. Something I mentioned, but I didn't talk much about, is the impact of climate variability, especially decadal climate variability, on the net primary production in the oceans and consequently on fish and shrimp captures. Very substantial impacts there also. All of this, as we saw, water and food insecurities caused by decadal climate phenomena can act as, and I have seen, I have written about this in my book on decadal climate variability, which came out in 2017. I show there several examples of these water and food insecurities caused by decadal climate phenomena acting as catalysts for socio-economic and political unrest, and also armed conflicts in many countries. So we need major research and applications programs to adapt to natural decadal climate variability. And along these lines, you may have heard about the government of India's Vaibhav initiative, where they want to involve scientists and engineers in so many different areas in research and development in India, people who are working outside India. And so we put together a report for climate variability and change, and the Indian Institute of Tropical Meteorology in Pune is going to be the lead agency for developing a community climate model that any of you will be able to use. And you can get involved even in the development of the model, because it will require, land surface model as a part of the climate model, climate system model. It will also require air pollution models and so on and so forth. So, you can also all get involved. We are also trying to start a large program in IIT Delhi on decadal climate variability, predictability, prediction, and societal impacts. So hopefully there will be opportunities in the near future for all of you or whoever wants to get involved in this kind of research and applications. So thank you very much. So these are here listed, my two books that Dr. Bhaskar had mentioned in the beginning. The one in 2017 is about worldwide societal impacts of natural decadal variability. The one coming out now is about the physics of decadal climate variability, so phenomena, mechanisms, and predictability. You can go to these websites which are listed here and see the kind of work that we are doing. And of course, at the bottom, there is my email address. You can send me an email if you want to discuss anything further, you need more clarification or help in any way. I'll be very happy to help. So thank you very much.
Thank you, sir. Now the session is open for discussion.
Yeah, I'll be happy to answer questions. Sure. Any question?
There are
Looks
few
like,
questions in chat box.
excuse me?
There are few questions in the chat box, sir.
Oh, okay. So hold on.
If you want, we will read it.
Yeah, hold on. How can I? How can I see the chat box?
Sir, shall I read the question, sir? Yeah.
Let me see. Okay.
Yes. Yes.
Yeah, I can see them. No, I can see them now.
Yes.
Okay, there is one here from Muralidharan M. Says correlating changes in cashew. Yeah. So again, this is one of the problems which I mentioned, that we can only access one number for cashew production over the entire country. And so we don't have much freedom to really go by trying to understand what happens regionally. You are asking about Kerala, you are asking about Tamil Nadu. No way that we can understand unless we have the data from those individual regions, right? So that is precisely what I was saying, that unless we get the data from individual regions, we cannot go further into this, trying to understand how climate variability impacts cashew production. Second one, Nahar Muhammad, particularly interested to know why governments decline to record and share relevant data. Yeah, so this is a question that it's really unbelievable that governments do this. But as I said, there are water issues for interstate water issues, international water issues. For example, in India has water issues with Pakistan, with Bangladesh, with Nepal. Within India, there are water issues among the various states. So maybe that's the reason why they are not, they are treating it as some sort of a national security issue, and they don't want to, they don't want to part with the data. They don't want to systematically measure things in many locations. It's a very sad situation. So all of us have to work on government officials and tell them that the benefits would far outweigh whatever problems that might occur as a result of sharing the data openly. Okay, Dr. Nereus Jenan Ekka, linking of rivers. Yeah, this is it's been talked about for a long time, since the independence of India. As to why can't, because you have, floods in some rivers, whereas there are droughts in some other parts of the country. So why can't you share the water? I mean, on the face of it, it sounds very, obvious. Why don't we do this? But now remember, you have to go back to geology. The rivers are the way they are because of geology. That because of the Earth's crust going up and down, what we call rivers formed in the valleys between two crests and so on. If you want to make the water flow against gravity, then you have to somehow use energy to do that. Water does not flow naturally uphill. And so one problem would be if you have to spend a lot of energy, electricity to pump water, is it worth doing it? Where is the electricity going to come from? Number two, the rivers evolved over many thousands of years, actually hundreds of thousands of years. And ecosystems have, that is something that I didn't talk about at all, is natural ecosystems like forests, swamps, wetlands, mangrove forests, right? They all evolved in response to how the river flows developed. If you abruptly stop water flowing down river, all those ecosystems are going to be affected adversely and they will die. You must have heard the phrase ecosystem services. We societies extract so many ecosystem services that if you abruptly stop water flowing, you will lose all those services. And as a matter of fact, you might create more problems than solve them by changing the course of rivers. Russia tried that. And you see what happened to Caspian Sea and Aral Sea, totally desolate. Number three, all this fresh water which flows into the oceans, the salinity is much lower than ocean water. And that changes the salinity, makes the ocean water fresher. And that changes the density of ocean water. It changes the gradients, north, south, and east, west gradients of ocean density, which drive ocean currents. And therefore, by driving ocean currents, you are also changing ocean temperature. So if you abruptly stop water flowing into oceans, that is going to change ocean salinity near the coast. It's going to change temperature near the coast. It may also have substantial impacts on climate. So, humankind has always, managed water for their own purpose without a lot of long-term thinking. So they built dams, they built canals, they use water to irrigate fields and so on. So I'm not saying that none of this should be done, but it is very important to understand the potential consequences before we undertake these very large-scale geoengineering projects. So the project is not a failure because it has not started. And it has not started because the problems, at least it is known that all this can happen. Bad things can happen. We want to make good things happen. They can perhaps happen, but so many bad things can also happen. So how do you mitigate the bad things? That is the problem. Okay, Karthikeyan, how does one confirm that a particular ecology phenomenon change is actually due to climate change? Very good question. And therefore, modeling is very important. So if you have models which are based on first principles, then, principles of physics, chemistry, biology, then you can simulate and see how climate variability and change might impact, let's say, ecosystems. So that is why modeling, simulation, and prediction based on those models are extremely important. Okay, Maithili Mailu. Okay. Okay, so I think that's all the questions. Is there any more? Okay, so there is one more here from Swapna Ray. Indian Ministry, MOEFCC, usually looks up for all these blah, 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 before approving environmental impact assessment draft, or they just, I don't know. I don't know how they do things. I mean, I don't think that they would only look for anybody's personal benefits, because, what are their personal benefits? I mean, we don't want to we don't want to unnecessarily accuse anybody of doing anything wrong or bad. But I don't know whether they take all this into account before approving potential environmental impact assessment statements or not. I don't know. Okay, any other question or comment?
Chat box.
Yes, Karthikeyan, you are absolutely right. It is always good to look for climate variability impacts before you ascribe anything to climate change and, oh, humans are doing this, humans are doing that. First, you should always check what is nature doing. Whether natural climate variability is making impacts that you can explain only through or entirely through natural variability before you start jumping to conclusions about human impacts. Yes. Okay.
Hello, sir.
Yes.
Sir, I have a general question. Sir, why
Sure.
scientists do not talk to politicians about the water shortage so that money they are wasting in this campaigning and all can be used for this purpose?
What is the question?
Sir, I'm asking that the money they are wasting in campaignings and all, the politicians.
Wasting in what?
Sir, in campaigning during the elections.
Oh, yeah, right. So, yeah, they want to get elected, right? And so they spend money in various ways to influence election, to influence people's, voting. Yeah, you were right. Why is more money not spent in adapting to climate variability and climate change? Very good question. I don't have any answer.
Okay, sir.
If there is no questions, we will thank Dr. Vikram sir for his excellent presentation on climate variability, and it is essential for this type of situations. And very sure, sir, that we will be in touch with you. Our students will be in impact with you for further research. Thank you, sir. Thank you very much. Thank you, sir.
Thanks for inviting me to give this talk. Okay?
Thank you, sir.
Thanks.
Monday we will meet you, sir.
Excuse me?
Monday we will meet with me, ma'am.
Yeah, Amita is giving a talk on Monday, right?
Yes, sir.
Yeah. Okay, very good. Okay, so thank you very much for inviting me, and I'm hoping to continue our contact with you in the future.
Yes, sir.
Okay. Thank you very much.
Thank you, sir. Thank you, sir.
Good evening.
Good evening. Good evening.